Okay, so we're now ready to start exploring conformal symmetry in D, oh, sorry, in D greater than 2 dimensions. So concretely, what are we going to do? Well, we are going to solve the conformal killing vector equation. So we're going to solve the boxed equation to find out the set of conformal transformations. And what we're aiming for is to determine the Lie algebra, the elements of the Lie algebra, and their commutators. Okay, now when we're solving a differential equation, there's always a little bit of guesswork. So you'll remember that when you were studying calculus, there's an algorithm that you apply to calculate a derivative, but to integrate, there's no algorithm. You have to experiment a little bit, try different changes of variables, different tricks, and try to see if you can integrate. Here we're solving a differential equation, which means we're integrating. So we also have to try little tricks, see what we can do to solve this equation. So for some of the steps that I do, it might not be obvious to you where we're going. Okay, and that's because actually it's a little trick that people figured out on how to solve the conformal killing vector equation. So for this section, what I would suggest is make sure you understand every single step. Remember that this was obtained by guesswork, so if it's not always clear exactly where we're headed, maybe that's not too surprising. There is some logic, and hopefully you'll see it by the time we finish. So let's call the conformal killing vector equation star. We're going to be using star a lot. And to start off, let's imagine that we act with d mu on star. What do we get? Okay, so in fact, sorry, let me just change these indices. Let's imagine that we act with d alpha, d beta on star. When we act on the very first term on the left-hand side of star, d beta up, d beta down gives us box. And then we've got d alpha, which will contract with the index on zeta alpha. So we just get d dot zeta. For the second term, now the d alpha up, d alpha down gives us box, and the d beta up contracts with the beta, which is down on zeta, to give us d dot zeta. So the two terms on the left-hand side are identical. We just get a 2. So make sure that you get that when acting with d alpha, d beta on the left-hand side of star. And then what is this equal to? Well, we've got 2 over d. That's just a constant. Let me pull that out. Then the d alpha d beta land up getting contracted by the Minkowski metric eta alpha beta. So we get box. And it's box acting on d dot zeta. Okay, taking everything over into one side, we get 2 minus 2 over d multiplied by box acting on d dot zeta, and that's equal to 0. Now notice, look at this factor. We have declared that we're interested in d greater than 2. Well, if d is greater than 2, it means that 2 minus 2 over d is 2 minus a number which is smaller than 1. So this number is greater than 0. So the only way that we can get a 0 from this equation over here is if box acting on d dot theta is equal to 0. So that's the first thing that we've learned. Okay, so good, we've learned that equation. Now the next thing I want to do, so let me maybe remove this over here. The next thing that I want to do is I again want to act on star, but now I'm going to act on star with d lambda. So let's act with d lambda on star on the conformal killing vector equation. What do we get? So we will get d lambda, d beta, zeta alpha plus d lambda, d alpha zeta beta is equal to 2 eta alpha beta d lambda d dot zeta. Let's make it 2 over d. We'll put the d there. Okay, so that's the first equation that we get. Let's move it over a little. That's the first equation that we get, and maybe let's just tidy up that lambda index. Good. Now what I'm going to do is I'm going to relabel. So I'm going to relabel beta to be lambda. Okay, so if we do that, what do we get? Well, we've got the beta, the lambda zeta alpha plus the beta, the alpha zeta lambda is equal to 2 over d eta alpha lambda d beta onto d dotted into zeta. So that's the second equation that we got. And we got this just by relabeling indices. We can obviously relabel indices on any tensor equation. And now I'm going to relabel again. So I'm going to take the first equation and I'm going to relabel alpha and lambda. So now we'll get d alpha, d beta, zeta lambda plus d alpha, d alpha, d lambda, zeta beta. And this will be equal to 2 over d eta. It will be lambda eta d alpha d dot zeta. Now notice a few things. So here we've got a d lambda, d beta, zeta alpha. Here we've got a d beta, d lambda, zeta alpha. So those two terms match. The d lambda, d alpha, zeta beta matches with the d alpha, d lambda, zeta beta. So those two terms match. And finally, d beta, d alpha, zeta lambda matches with d alpha, d beta, zeta lambda. Okay, so now let's call these equations. This is equation 1. Let's call this equation 2. And let's call this equation 3. And now what I'm going to do is I'm going to take a linear combination of these equations. So let's study 1 plus 2 minus 3. So what does this give us? So if we add 1 and 2 and subtract 3, well, it's pretty clear if we're subtracting 3 from 1 and 2, the red term will cancel with the red term, and the blue term will cancel with the blue term. So we'll get 2 times by the green term left. So we'll get 2 d lambda d beta zeta alpha. This will be equal to, now we've got a 2 over d that's common to all of the equations. So let's put 2 over d outside. But we've got an eta alpha beta d lambda plus an eta alpha lambda d beta plus, and we've got an eta lambda beta d alpha, and that is acting on, so this is acting on d dot zeta. Great. Okay, and now let's give this equation a name. Let's call it dot with circle. And what I want to study now is I want to take a derivative of this equation. And let's take a derivative with respect to alpha. So let's take d alpha acting on this equation. So what do we get on the left-hand side? Well, we've got 2. We've got d lambda. We've got d beta. And then the alpha index contracts with the zeta. So we've got d alpha d beta acting on d dot zeta. This is equal to 2 over d. Now, if we act with the d alpha, you can see that the eta is going to bring the eta alpha beta will bring the alpha index down and turn it into a beta. So we've got a d beta. Then we've got d lambda, that doesn't change, plus another eta alpha lambda will bring the alpha down and turn it into a lambda. So we've got a d lambda, d eta. And then for the last term, the eta lambda beta stays unchanged, but the d alpha up contracts with the d alpha down to give us box. And this is acting on d dot zeta. And now here is the important thing. We derive this boxed equation up here. Let's call it, I don't know, let's call it triangle. Box on d dot zeta is equal to 0. So this term, which gives us box on d dot equal to 0, this is equal to 0 by triangle. Okay, so that equation, box on d dot zeta equal to 0, tells us this term in the conformal Killing vector equation vanishes. And then you can see that every term is proportional to d lambda, d beta acting on d dot zeta. So the equation that we get is 2 minus, there's two terms here, times by the 2 is 4 over d, and this is multiplied by d lambda, d beta, d dot zeta is equal to 0. Now, recall again. If d is greater than 2, that means that 4 over d is less than 2. And that means that 2 minus 4 over d is greater than 0. So the only way that this expression can be equal to 0 is if d lambda, d beta, d dot zeta is equal to 0. So you can see that triangle told us that if we act with box on d dot zeta, we got 0. What we've now managed to prove is that any two derivatives acting on d dot zeta is equal to 0. Great, we'll continue in a moment.